One wrong repair weld can destroy a 5 crore compressor. And the scary part? Most failures don't happen during welding. They happen months later in service. Today, I'll show you how to prevent that using real engineering logic. Slide 1. Why repair welding is critical. Repair welding is not normal welding. Here, the material is already heat-treated, already stressed, and when you weld again, you're disturbing the entire metallurgy. That's why failures like SSC, SEC, brittle fracture can happen if governance is weak. This is why repair welding needs strict control. Slide 2. What is repair welding? Repair welding is a controlled 3-step process. 1. Remove defect. 2. Re-weld using qualified procedure. 3. Re-inspect. And this applies to weld defects, casting defects, machining damage, field modifications. It's not fixing, it's restoring integrity. Slide 3. Importance of tempering. Here's where metallurgy becomes dangerous. During repair welding, the H/Z can become hard, brittle, crack-prone. Especially in RMO steels and sour service, tempering solves this by reducing hardness, relieving stress, improving toughness. Without tempering, you are creating failure zones. Slide 4. PWHT versus tempering. Many engineers confuse this, so remember clearly, PWHT equals stress relief plus hardness reduction. Tempering equals microstructure improvement. PWHT is broader. Tempering is more specific, but both are critical depending on material and service. Slide 5. Hardness control. Most important. This is a golden rule in oil and gas. Maximum hardness equals 22 HRC in sour service. Why? Because higher hardness, higher risk of SSC. And SSC is not gradual failure. It is sudden, catastrophic failure. That's why hardness testing must be done in weld metal. Slide 6. Heat input control. Heat input is like a balance. Too high, grain growth, weak material. Too low, lack of fusion, defects. So WPS must define preheat temperature, inner pass temperature, heat input. Good welding is controlled energy, not just skill. Slide 7. Repair workflow. This is the correct workflow. Defect engineering review, approved WPS, execution PWHT. And here's the key. Every step has a quality gate. Also, major repairs require client approval, no shortcuts. Repair limits. You cannot repair endlessly. Codes limit. Repair cycles, typically 2 to 3. Repair depth, 10 to 25% thickness. Total repair area. If limits exceed, engineering decision required because repeated welding damages material permanently. Slide 9. Rotating equipment risks. In real applications, pump casing, distortion, vibration. Compressor casing, crack propagation. Small bore piping, highest failure rate. And here's a pro insight. Small bore failures are the most common in packages. Slide 10. Common failures in industry. These are real mistakes engineers make. No client approval, using wrong WPS, skipping hardness testing, no documentation, no dimensional check, skipping PWHT. These mistakes lead to rejection, delays, and failures. Slide 11. Interview questions. If you want to crack interviews, remember this. Repair welding is risky due to hardness plus stress. PWHT reduces stress and hardness. Hardness testing is mandatory in sour service. Repairs are limited to 2 to 3 cycles. Documentation ensures traceability. Answer like this, and you sound experienced. Slide 12. Golden principle. Here's the most important line. Repair welding must restore original properties, not just fill the defect. If you understand this, you understand real engineering. Slide 13. Systematic approach. Always follow this sequence. Repair, review, WPS, weld, PWHT. Skip one step and failure risk increases. This is not optional. It's engineering discipline. If you want to become a top engineer in oil and gas, you need to think beyond drawings and understand failure mechanisms. Like this video. Subscribe for deep engineering breakdowns. Comment weld if you want a video on real failure case studies. See you in the next one.